Hey, welcome back to 15-Minute Math. Today we're going to be finding limits analytically, and we're going to focus on continuous functions. So in the past couple videos, we've been evaluating limits, or at least estimating limits, through various methods. And you can see a couple of those on the screen right now. We have, graphically, we can evaluate limits, and using tables, we can evaluate limits. But, in a lot of ways, these aren't really evaluating the limits. They're really more just estimating the limits. We're just trying to pick up on a pattern and kind of just complete the pattern. Now, those patterns may not hold true. We're not really proving that those are the limits when we use those methods. They really should be called estimations of limits. And so when we can find the limit analytically, we can be much more certain that this actually is the limit that we're looking for. So when at all possible, it's best to find limits analytically. Although, to build an intuition of what a limit is, it's good to use these methods first, but we're going to try to maybe graduate to some more sophisticated methods. So as we go on, we're going to see some nastier functions that we're going to need some different methods than what we use in this video. So we're going to keep it fairly vanilla here with the type of functions we're going to see. And so we're going to focus on continuous functions. And when I say continuous, I just mean like in the very elementary definition. When you first heard about continuity, probably in Algebra 1, I'm sure your teacher said, okay, well, a function's continuous if you could draw its graph without picking up your pencil. And that's kind of what I want to focus on today, those sorts of functions. And so when I say continuous, I'm not being very rigorous in my definition of what constitutes continuity. We're just thinking about that very elementary definition. So functions that fit that definition, we're going to use this sort of procedure that we're going to go over today. Or at least we can use it if where we're evaluating the limit, the function is continuous in that region. We'll talk about that towards the end. So let's kind of revisit some of the old methods and then, maybe briefly discuss why they're not that great, and then we'll move on to what we really want to talk about today. And so for our table method, you could take your function 1/2 x plus 2, and we want to evaluate the limit as x goes to 4. And remember, the idea is, well, okay, I can just make a table. I can use values very, very close to 4 and see if I can pick up on a pattern. So 3.9, you can see my output, 3.99, there's the output. And then as I get very, very close to 4 with my inputs, well, actually my outputs are getting very, very close to 4 as well. And then you can see it also happens from the other side. As I go from the right and go towards 4, well, my outputs are going towards 4, and so it's very, it's reasonable to say, okay, well, the limit must be 4. That's what my pattern says. But, really, we're just picking up on a pattern. There's really nothing to say that it couldn't be like 4.000000001 or something like that, right? I mean, maybe these values are getting very, very close to 4.0000001. If it's very, very close to 4, then it's also very, very close to this number after all. So, this really is an estimation. It's not, you don't want to rely on tables if you don't have to. And very similar thing here graphically. Let's look at the limit of this function as x gets closer to 2. And you can probably do that thing where, okay, let's just like slide our fingers along the function until they meet at 2. And what's the corresponding function value, or y value, I should say, and it looks like 7, so we're going to claim that the limit is 7. But again, if we're just looking at a picture, how do I know that's not 6.999999? Right? There's really no way to tell, especially how zoomed out we are. And with Desmos, it helps a little bit because you can zoom in to almost an arbitrary level of precision. But in this case, it's kind of hard to tell. So it would be very, very nice if we could just come up with a method to do this analytically. And before we leave this page, maybe we should notice something. What if I just took this function, and I'm going to go ahead and call it f, and we just plugged in the value that we want to evaluate the limit at, this x value here. What if we just evaluated f of 4? Well, that'd be 1/2 of 4, and then add 2. Well, 1/2 of 4 is 2. If you add 2 to that, you get 4, which is precisely what our table suggested our limit should be. And you could do the same thing here. We'll call this guy f as well. I'm not very original. 4 times 2 minus 1. Oh, I should have wrote f of 2 there. Well, notice that's 7, which again is what the graph suggested our limit should be. And so we may already be picking up on a pattern here. If I just evaluate the function at my limiting point, it gives me the limit. At least it seems like that should work. So let's go over to Desmos and let's see when that works and when that doesn't work. So what I've got right now is, 1/4 x squared is graphed. I've got a point that I can slide around. And we're going to evaluate the limit as x goes to 2. So what values is my function approaching as I get closer and closer to 2? And you can kind of do that whole thing, drag your fingers. It certainly looks like it would be 1 here. I've got an epsilon and delta range all dialed up. So let's use our epsilon delta definition and just kind of revisit that maybe a little bit. So remember, our epsilon delta definition basically says I can make this purple epsilon range as small as I like. I should be able to, and I should still be able to get a delta range so that as soon as my point gets inside of this delta range, it's also inside the epsilon range. So you can see my delta range right now is not small enough, right? Because if I'm cruising in from the left, when I get inside the delta range, I'm not also inside the epsilon range. So we need to make our delta smaller. It looks like that'll work, right? Now, as soon as I get inside of delta, I'm also inside of epsilon. And the rule, actually, it doesn't work up at the top there, does it? So maybe we should make it smaller. There we go. That'll work. Now, as soon as I'm inside of, because remember, limits have to work both ways. So I can't just go from the left. So from the right, this also now works. And we should just be able to, the idea is we should be able to do this no matter how small epsilon is. And you can kind of see, no matter how small epsilon is going to get, I could always just slide delta, make that a little bit smaller, and I'm always going to get this to work. And, we thought about this in the previous videos, like just kind of like boxing in the limiting point here, and so it can't escape, so to speak. And if I can box it into a certain value, we say that is the limit. And so in this case, the limit really is 1, because we can... Obviously, this is a little bit experimental, but you can kind of see we're going to box this in, and that box is going to get smaller and smaller, centered around 1. And so the limit is 1. Now, could we have just plugged in 1 to our function and gotten the answer that way? Well, let's go over to our whiteboard here, and let's just try it out. So it was 1/4 x squared, rather. And we were going to evaluate that at 2. And so let's just find f of 2. Well, that's going to be 1/4 of 2 squared, and that certainly is 1, which is what we claimed our limit was, if you recall, right? It's 1. So our idea works there. So far, this is looking promising. It looks like we could just, we don't need to use tables. We don't need to use graphs. We'll just plug everything in. Why not? It seems like it's worked. It's 3 for 3 so far. Let's look at maybe a different function here, and because of the way I've done my Desmos graph, I've got to change some labels around real quick. So now we're going to call this guy f. Let's zoom out. Okay. I think I have to turn my points on. That one and that one. There we go. Okay. So now we're ready to look at this. So you can see I've got this piecewise defined function where I've got a linear function on the right side of 2. I've got maybe a cube root function, it looks like, on the left side of 2. And there's a discontinuity here right at 2. So notice this graph is not continuous. I could not draw this graph without having to pick up my pencil, right? This is not a continuous function. Now, it is continuous everywhere to the left of 2. It's continuous everywhere to the right of 2. But it's not continuous literally at 2. And so let's try to evaluate the limit at 2. And remember, we've seen these in the past, where if I approach from the left side, it looks like the limit's 2. But if I approach from the right side, it looks like the limit's going to 4. And if you recall, in an earlier video, we tried to apply our epsilon delta definition to this, and we said it just can't work. Because, like, if I'm going, well, maybe let's go up here so I can actually zero it in. I can get my epsilon and delta definition to work here, For example, I could make delta just a little bit smaller. Actually, no, I'm already good, right? So from the left, I can make delta even a little bit bigger. So right now, my definition works, but not from the right, or it works from the right, I'm sorry, but not from the left, right? As I approach from the left, if I get inside the delta range, I'm certainly not within the epsilon range. And there's no way I can make delta small enough for that to work, right? Because I can get infinitely close to this point. So we just said in a previous video, this limit just does not exist. It doesn't exist. But let's look at the function value of this. If I wanted to find the limit at 2, our previous thought was we could just find the function value, which if I find the function value, it looks like to me it's going to be 4, which does not match our answer, right? Our answer from a limit standpoint does not exist, and the function value is 4. And so we found the first time that the idea that we could just plug the number in, we could just find the function value, that doesn't really work. And hopefully you picked up on why it doesn't work. It's the discontinuity that really throws us off. If there's a discontinuity, we can't just blindly plug in a value. Because, as you can see, the limit may not even exist, whereas the function value might exist. My function value here would be 4, but my limit doesn't exist. And so you can't just always plug your limiting number in. You really do have to think, okay, is my function continuous? If there's a jump discontinuity, that's going to throw you off. And we're going to look at one more scenario, and I'm going to pause while I get this set up on my Desmos graph. Okay, so now we have a linear function, but it is defined piecewise, and I know it's hard to kind of parse what you see there on the Desmos window, so maybe let's go over to the whiteboard and write this function definition down. Go over here so I get some more space here. So my function is defined like this. It's f of x equals, and now actually I forget the function rule. Looks like 1/2 x plus 2. So it's 1/2 x plus 2 if x is less than 2. It's 1/2 x plus 2 if x is greater than 2. But it's equal to 5 if x is equal to 2. So we've got this kind of goofy definition of our function. So notice that f of 2 right now, it's 5, right? If I wanted to evaluate this piecewise function, I'm using this rule since x is equal to 2, and it says that my function is equal to 5 at that point. And so 5 is my function value, but is it my limit? And let's kind of go back and let's evaluate this limit at 2. Well, if I approach from the right side, it looks like I'm going towards 3. And if I approach from the left side, it again looks like I'm going towards 3. Remember, limits really don't care about the actual function value, and limits don't even really care if the function is defined at that point. All we care about is the trend as we get closer and closer to our limiting value. So we're trying to find the limit as x goes to 2, and we're going to say that limit is 3, and we could even pull out our epsilon and delta definition, and as I box in this point, as I get closer and closer to 2, Desmos won't let me actually get on 2, but I can get pretty close. If I do that same process where I'm going to make epsilon small, and then how small do I need to make delta, I can still do that, and I'm going to close in. This box is going to close in on 3. It's not going to close in on 5. So my limit is 3, and my function value is 5. So what's the moral of the story here? Well, if your function is continuous, just plug the number in. That's much easier than doing tables or graphs or anything else. But you really do need to be careful. If your function is not continuous at that point, then you really can't do that method. So we're going to develop a lot of different ways to evaluate limits, but the very first thing you need to check for is it continuous? Is the function continuous? And if so, just plug it in. That's the easiest way to do it. And if you can do it, you should do it.